explain this point again.
So do you know the concept of temperature inversion?
No, sir.
Do you know the dependence of mobility on temperature?
Yes, sir.
So what happens to mobility
Okay,
as temperature increases?
mu proportional to t to the power minus 3 by 2. Is it that?
Yeah.
So the
And
inequality will, yeah. Okay, okay.
is there anything else in terms of temperature that mobility is dependent on?
I mean, there are two kinds of scattering we consider,
Yes.
and it
Yes.
increases for 3 by 2. Then
Equality
it
is scattering and
starts
beta is scattering.
it's both plus
Yes.
and minus.
Yes. So as temperature increases, the scattering also increases. So mobility actually, overall current actually degrades.
Yes.
Okay. This is at high voltages. However, when you're operating at low voltages, the total number of carriers that you have in the conduction band, they are not much. So when you increase the temperature, that carrier boost is much more than the scattering that would have happened because of lattice vibration and anything like that. Okay. And therefore, at low voltages, higher temperatures lead to better current.
Yes.
Sir, can I just repeat that? Like how higher voltages can lead to better current, even though I mean your mobility is decreasing. So
Higher voltage is always better current, is it not?
the higher voltage is better current, but higher temperature will like reduce.
So what happens at low voltages, the voltage is so low that the gate overdrive, let us say, is not sufficient. Even if the gate overdrive is sufficient, we say that the number of carriers that you have in the conduction band to be able to conduct the current, that is not much. There are carriers, inversion is already set in, we know that, but even then there is something missing. As you increase the temperature, more carriers come into picture.
Right.
Carriers have more energy now, so
Yeah.
they move faster.
Also, sir, I mean temperature is also actually decreases the threshold voltage. That is might also be a factor.
Yeah, so see, threshold voltage reduction is also a consequence of this effect that आपका number of carriers बढ़ जाएंगे and all that.
Yes.
Looking at the different definitions of threshold voltage, see, all these are different ways of pointing at the same phenomena.
Right.
Current increase hona, VT reduce hona, all they are one could say that because current has increased, therefore VT has reduced. Because VT ki definition is 1 microampere of current for a 1 micron width device.
Okay. Right.
है ना? So yeah, Raj. Is this part clear? Hello? Temperature and impact of temperature and voltage on circuit performance. Is that part clear? Rajneesh, you have a question?
Sir, slide is not visible.
Sir, when this in this you have written that the VDD is higher and the temperature is low. So though our device is becoming faster, sir, but the threshold leakage will increase, no, sir.
Yeah,
no,
threshold leakage on fast devices is known to be higher.
Yes, sir. Yes, sir. We have to compromise with.
Yeah. That is known to be higher.
Okay.
So now tell me, if you have to verify, then what will be the PVTs at which you will design and verify your, PVT means process temperature and voltage, for which you will design and verify your circuits. Hello?
Slow, sir.
Slow. What about voltage?
Slow with low voltage.
temperature?
High.
High temperature. So, have you checked your assignment 3? They've asked you to characterize at multiple PVTs.
Yes, sir.
Yes.
So now can you identify and relate why so many PVTs are being asked for?
Yes, sir.
They're all about these various corners. And also what you will see is that for some parameters, like for timings, delays, slow everything, putting everything to slow leads to worst case result. But for some other parameters, putting everything to fast would lead to worst case results. And in terms of leakage, it's a mix of slow and fast, because you want high temperature to see worst case leakage. Are you able to see this?
So the worst case in case of in case of fast will be for whole time like violations.
Yes, contamination delays will be worst in the fast, low temperature and everything.
Okay, sir.
Propagation delays will be worst in slow, high, low voltage and high temperature. Subthreshold leakage, as we rightly pointed out, is higher when you have fast NMOS, fast PMOS, when VDD is also high. But for high leakage, we need to have the higher temperature. So the temperature is related to the slow temperature, 125 degrees Celsius. That is where you need mix of different PVTs to overall characterize your designs. That is why this long list of PVT is there. So is that all? Is that all that we need to worry about, or is there something else?
So can you explain the slide again?
Which slide?
So the slide important for us.
This one?
No, sir. I meant like the one you were currently on, like last time. No, sir. After that. Yes. So when I asked the doubt, we were on important quarters, like for purpose cycle or cycle time, you're using slow. And yeah, this one. Can you just explain this again? I mean, how all these corners are suited for these type of purposes?
Okay, so we just saw na delay are worst when NMOS is slow, PMOS is slow, VDD is low, and temperature is high.
Okay, I saw that cycle time.
It's just tabulating it in one form. That's it.
Okay. Right, and obviously it will consume more power when it's in the fast curve.
Yeah, power would also be higher, also because of leakage being higher. When your voltage of operation is higher, it is CV square F. So the capacitance is higher when the devices are fast. V is higher. VDD means we want to increase CV square F, so VDD has to be higher. And we know frequency is highest when the temperature is low. So CV square F is highest when, or power is highest when everything is towards the fast side. Okay?
Yes, sir.
Yeah. So someone of you already pointed out that, okay, we can have all these lots. So in reality, what you get is not rhombus. What you get is actually an ellipse. And on that ellipse, you define what is called as 1 sigma ellipse, 2 sigma ellipse, and 3 sigma ellipse. You say everything within this is considered as typical, and this part is slow, let us say. Okay, so all models, SS, FF, all that rhombus that we looked at, it is a fitting exercise. You have to arrive at a rhombus over here, which would be safe for designing purposes. There may still be some lots which will be out of this rhombus, and you agree that on those lots, you accept some extra yield loss. Okay. In addition to that, see, whichever lot I have designed at, suppose a lot is placed here, you will see that there will be variations on that particular wafer itself. These are called device variations. So until now, we were looking at lot variations. Now these are called device variations. And to validate a design with device variations, you go to the SS corner or FF corner or whatever corner you're talking about, and you run Monte Carlo there. What is Monte Carlo?
Sir, if there are like more number of inputs, I will be using each input one after the other to get the output.
Yeah, Monte Carlo analysis is an analysis in which you will vary different parameters which are known to exhibit variations. So what are the parameters over here that we know will exhibit variations? Intrinsic parameter over here that will exhibit variation. Doping, L effective, W effective, stuff like that. So you vary all those parameters for different devices and randomly place those variations on different devices. Then when you simulate, what you will get is this red shaded circle around that lot point. It is the sample of transistors that could be manufactured on that particular lot.
Sir, can you explain this again? Actually, I was not able to get it. This. What we are for a particular lot, what we are doing exactly here?
So, abhi hum baat kar rahe the na, we were just talking that if there is a wafer, even on that wafer, there could be variations that could happen in a device which is manufactured towards the top of the wafer and then a device which is manufactured towards the right side of the wafer.
Yes, sir.
So it means that for even a lot, there will be other device variations which will come into picture.
Yes, sir.
So how do you validate those? So one part of validation, we said, okay, we will test or characterize and design our stuff at circuits at SS 1.1, 125. Well, SS, low voltage, high temperature, and all that. We just agreed that we will do that. But for final circuit verification, you also need to take into account device variations. And that is what you will do by the means of running Monte Carlo simulations. This is called as Monte Carlo analysis also, in which different variations are applied to different transistors so that the example that we just saw, that one PMOS is fast and the NMOS is slow, those situations can appear even in a fast lot or even in a slow lot, where they were expected to both move in the same direction.
So
Okay.
sir, like when at the starting I was taking the PVT variations in the law for a lot, basically I said that okay, my NMOS will be slow, and this VDD and temperature kind of way. So by that I had considered the lot variations of the lot thing, and now even I'm going once I pick up a certain corner, rhombus corner, then I'm going into that particular corner.
Yes.
And doing the same exercise of PMOS, low PMOS, NMOS, then and VDD temperature.
Yes. Again, injecting variations in there.
Okay.
And seeing how the devices in this particular lot can lead to the change in my circuit functionality.
Okay. So, sir, like when for example, in the Virtuoso itself, when we are doing the simulations with the ADEL window, so when we are selecting the sources, that at that time when we are selecting the slow, and the temperature, that are basically the lot basically parameters.
Lot variations. Yes, they are lot variations. Okay, Rajneesh.
Sir, so in conclusion, we can say that within this slot, there are this is the wafer, and this wafer has this four corner devices, that fast, slow, and this four. And there are, sir, this sir, in this lot variation, sir, there is 4 possibility of devices, sir.
In the lot variation?
So this graph here is the lot variations. So here basically there is 4 possibility of
No,
devices.
there are infinite possibilities of devices. That is why we've made this ellipse there.
So in this there is no fast, fast, slow, slow.
There is the corner points, we call them fast, fast, and slow, slow.
Okay,
The
sir.
corner points of this ellipse, we call them as fast, fast, and slow, slow. But there will only probably be a few lots in those corners. Majority of lots will be enclosed in the rhombus there.
Okay, sir.
Hmm?
Okay, sir. Okay, sir.
Okay.
Excuse me, sir.
Yes.
So for this left graph, so that is the lot variation.
Yeah, left and right both are lot variations only.
But then
On the right one, I've just made this red circle, which is device variations.
so what is the y-axis in both of them?
For the left graph, the y-axis are threshold voltages, and for the right graph, the x and y-axis are currents, ID sat.
Okay, so but we could run this Monte Carlo simulation on the left graph as well.
Yeah. You just
Okay.
choose a lot and you run Monte Carlo variations, and you will
Okay.
get a distribution of all these points.
Okay, sir. Okay.
Okay. Yes, Deepank.
Good afternoon, sir. Sir, my question is for TT, sir, does the foundry provide us a real T, because we cannot be very sure that which is the most middle point always. So every time you manufacture, the middle point also might vary. So according to me, the TT should be calculated theoretically, and with reference to that, we should decide FF and SS, or the foundry only provides every time the TT parameters
The
for
foundry
that.
will give you the lots always. Even the SS and FF lots, the foundry will give you. You don't decide as a designer.
No, sir, my question was like TT should be an averaged out value of all the corners, right? Because
Every foundry may have a different way to arrive at TT, Deepank. Some foundry may say that, okay, this TT will be my target.
okay.
Okay, suppose today you want to design in 3 nanometers. The technology is not even there, or even if it is there, it is in a prototype stage. You do not even know what kind of variations will finally happen, not happen. So where you will finally place your TT, you still not figured out the final devices or the final materials that you will use in your gate dielectric and stuff like that.
Right.
Okay, you have a prototype technology running. So in such cases, the models will be called paper models, largely paper models, where
Correct.
we're talking about specifications. But
Correct.
as the technology matures, for example, if today you would want to talk about 18 nanometer or 22 nanometer or 28 nanometer, technology is very mature. So now TT is actually given by the lot, by the process, that okay, there are majority of wafers which are being manufactured in this place. So this is my TT.
Correct. Correct. So my question is that, yeah, we were doing the simulations in Eldo, so we had the files with us, and there were TT also in that. So, but in the real life, that TT might change over the time.
Yeah, so
Okay.
in real life, yeah, in the evolution of a technology, it will definitely change.
Okay. Sure. Okay. Got it.
But once the technology is frozen, once the process is well in control, and the foundry has defined that this is my TT, then that TT then remains constant. Then if you make a lot and it is towards fast, you say it is not TT. That's it.
Sure.
But as the technology evolves, TT would change. Yes.
Sure. Thank you so much.
Yeah. So is the question clear to others also? Is the answer clear to others also?
So like in both the graphs, after we have the foundry has provided us with the basically the lot corners, then this red basically curve is that we are doing by ourselves for the Monte Carlo for the device kind of analysis on that particular lot, right?
Yeah.
Okay.
And what he was also asking was, will TT always be constant? Is TT a hypothetical value or driven from the process? So what I responded was that when the technology is not very mature, TT would be paper models. In fact, all the corners will also be paper models. But as the technology matures, TT and all the other corners will be silicon driven models. And the positions would change over time. Yes, Devajit.
Sir, just to confirm one thing, in both the graphs, sir, the FF and SS would be reversed, right?
Yes. On the left graph, FF would be towards the bottom corner, towards the origin side.
Yes, sir. And
on the right graph, it will be the SS will be towards origin side.
okay, sir. Yes, sir.
Yeah.
Thank you, sir.
Good observation, Devji.
So because saturation current is more on the right side.
Exactly. So I can confuse you in the mid sem or end sems and tell you कि अच्छा बताओ कहाँ पे FFTT है. So you have to carefully look at the axis and then decide.
Okay, sir. Thank you.
Okay. So in addition to these TT, SS, FF things, we also have what is called as FFF and SSF lots or points. They are essentially the result of when I run Monte Carlo on FF and SS. I see that the worst case NMOS and PMOS combo can happen over here. So when you are, verifying small circuits, you may want to verify them over these points also. You do not characterize them because in characterization part, usually a small circuit is not an end in itself. You would have many circuits cascaded one after the another, and the overall delays would never be at FFF or SSF. But when you're just verifying your circuits, you may want to verify them at these functional points also. Not all foundries provide it, but quite a few foundries do provide these functional models. Okay, so they may call this as FFG, SSG, SFG and FSG also. But yeah, they may also provide these functional models in addition to that. Okay.
Sir,
now, yes.
Sir, how are we supposed to do this Monte Carlo simulation in the simulator, sir? In Cadence.
Yeah, so you can look into the user manual. You just have a command called .mc.
Okay, sir.
Okay, you just use the command .mc. You tell which parameters you want to vary, and you tell how many number of simulations you want to do. So it will run the Monte Carlo simulations for you.
Okay, sir.
It is available in the user manual. Okay. So now, see, we know that a device may be manufactured, let us say, fast. But on fast, we also know that the leakage is very high and the delays are much lesser. So you signed off, you designed something to operate at 2 gigahertz. Now a die is manufactured or a lot is manufactured which is operating at 3 gigahertz. Now overall ecosystem, आपको पता है 3 gigahertz, you cannot really operate the system at 3 gigahertz because there could be resonance issues, there could be inductive effects which would come into picture and so on. So you anyway want to operate the particular die at 2 gigahertz. But the devices are fast, so you say, and my leakage is very high. You say, oh, can I do something to arrive at 2 gigahertz instead of 3 gigahertz? But I reduce the leakage. So what would you do? You can do multiple things. You can, for example, apply body bias. What happens when you apply reverse body bias? Devices start to move towards slow. Then VT starts to increase basically. Another thing that you can do is you can reduce the voltage of operation. You can say, see, I wanted to operate at 2 gigahertz at 1.2 volts. Now at 1.2 volts, I'm already getting 3 gigahertz. Why not operate at 1.15 or 1.12 volts? And I will come to 2 gigahertz. And now because I'm operating at a lower voltage, I will also consume lesser power. So these two techniques, so this is where you are changing the body bias, is what called adaptive body bias. And the other one where I said that you could lower the VDD, or if you're on the slow lot, you want to improve the performance, you could increase the VDD a bit, because you know that at higher VDD performances are higher. So that is called adaptive voltage scaling. Okay, so these again are areas of active research. There is lots of work happening. There are even production. These technologies are even production, where dies are trimmed to operate at lower voltage or higher voltage depending on where they were manufactured at. So at the time of test, you see what is the operational frequency and you trim them. What is the leakage and you trim them appropriately. Okay. Raghav?
So the body bias was applied for the fast and the voltage for the slow. So kind of.
I could apply voltage for fast also. I could lower the voltage and reduce the overall power consumption.
Okay, right. Both these techniques are available for the corners.
Yeah.
So by using these techniques, I'm trying to basically move the devices towards a typical corner.
Yes. I'm trying to bring the device back into my specification for, say, let us say leakage or power consumption or timing or whatever.
Okay.
Okay.
But
so process compensation, you will see, is used in a large number of products today already. It's not a new concept that we're talking about any longer. Okay. Something else also, Raghav?
I mean, so this body bias thing was considering this body bias can basically further create more complications, won't it? Like, I mean,
like,
I'm not able to exactly pinpoint, but I think that something like it can lead to like further because earlier when we were considering when we were doing the substrate taping and substrate tapping and we're connecting the source with the body, we are sort of those latch up effects and many other things can pop up.
Yes. So very, very good, Raghav. I'm so happy that you're able to anticipate the problems that can come with body bias. So in terms of forward body bias, you have to realize that you cannot really forward body bias your PN junctions beyond anything beyond 0.2 or 0.3 volts, because otherwise the leakage currents would kind of run off. Similarly, on the side of reverse body bias, there would be constraints on how much reverse body bias you can put. Again, because otherwise band-to-band tunneling will kind of run off. There will be lots of current that will flow from the source to the substrate or drain to the substrate. So you cannot really do a lot of body bias. So very good and very interesting observation. However, in advanced technologies like FD-SOI, fully depleted SOI, so there is no junction in the source and drain region. There is simply a buried oxide. So since there is no junction, so there is no concept of junction leakage per se, and junction leakage cannot increase. So you can apply whatever amount of forward body bias or reverse body bias that you want to.
So you are talking about here the SOI technology.
Yes.
Okay.
The fully depleted SOI, not even partially. If you were on partially depleted SOI, then again you will face trouble because junction would be there. Only in fully depleted SOI, you can actually go to very large range of body bias voltages.
Okay. Yes, sir.